All right, why don't we get started? So I'm back in the country this week and we're ready to start Unit 5 here. Um, just a note on Unit 5 and 6. So we're going to start we're going to start looking at a special type of neural network called convolutional neural networks. So last week we started kind of looking at neural networks here, just generic neural networks. And it's important because almost all AI today is based on those traditional neural networks. And today we're going to look at, or this week, we're going to look at a special type of neural networks called convolutional neural networks. They have some special layers and some special formats to them to handle images. We used to spend 3 or 4 weeks on these because these were the big thing in AI maybe 4 or 5 years ago. This was really cool stuff that we could do here. I've dropped that down to 3 weeks. Last year, I dropped it down to 2 weeks. This week, I'm dropping it down to 1 week here. Because so we'll spend 1 week on convolutional neural networks, and then next week, again, it'll be all focused on image processing. So the next week we'll talk about generative AI related to like image generation, video generation, stuff like that, which builds a lot on these convolutional neural networks and these layers. So the layers we learned this week will actually be used next week when we look at generative AI sort of stuff. And I think you're probably all familiar with some generative AI systems, although there are always new ones. So one thing for this week's discussion, I want you to find any sort of article on image recognition or generation sort of stuff here. And again, if you have a new website that's out there that you use to generate images or particularly videos, I haven't used some of the new video ones, post that to the discussion so people can start trying it out, and we'll look at these more next week here. So again, besides articles, feel free to find a website used to create images or videos or stuff like that. And again, it kind of loose with that what an image is. I saw one that could be used to take almost any image and make it into a coloring book image for kids to color, that sort of stuff. So I mean, there's lots of different ways of using these images. I see a lot where I do a lot with historical photographs, and sometimes we're just using that AI to take historical photographs and fill in missing details or, fix it up in some ways or another. So again, when I say create, I'm pretty loose with that definition there. So, okay. So we're going to try to jump into convolutional neural networks this week. I'm just going to go to Unit 5 and go to this learning resource and get started on that. I'll apologize right now again because I've taken 2 weeks worth of stuff and put it together here. So there's just a lot of stuff here. You might still see, I tried to remove all references to like Unit 6 or a future unit where I moved this from, but in some of the videos, there are some places there might still be references to stuff here. So just be aware that some of this, especially the older videos, will have references to old stuff here. Okay, so convolutional neural networks. One of the great resources if you're learning neural networks and some of this AI stuff is MIT's videos. MIT offers a course in this stuff. And again, it evolves just like this course every year. It's usually their S191 course here. And again, this is a version from it a few years ago where they were talking about, again, they, like me, were spending a lot of time talking about convolutional neural networks and how that works. So this was from 2019, again, 5 years ago when this was really big. their new, and again, later on, we'll jump into some of their new stuff within this course, whether they're talking about transformers and stuff like that. But the MIT course, and I think they do a very good job of walking through this sort of stuff and having one of their TAs describe it. I'll just warn you, this is MIT, so like they're doing this in day 2 of their advanced course, where we're doing it in unit 5, just so you know.
Deep learning for computer vision. So, motivate. I think we can all agree that vision is one of the most important human senses. Science people rely on quite a lot for everything from navigating in the world to recognizing and manipulating objects to interpreting facial expressions and understanding emotions of
Jump to this one. I'm not going to play, of course, this whole thing. I just want to highlight just a couple of things. So again, she'll walk through, and we'll walk through some of the same stuff, but I think, again, their view on how this works, they do a very good job trying to do this stuff, going through these examples of convolutions and stuff like that. They are MIT, so they'll get a little bit more in the math of this than other stuff. But again, I think if you want just one place, I would just watch this one video, 40 minutes, and go through that here. Okay, so that said, let's work through the same sort of material here. So again, images, video, vision, all that, it's really key to our understanding. And a lot of this neural network stuff is kind of inspired by the brain, and we've been trying to do that. So when we're trying to understand how we can process images, one of the things we do is look at the brain and the visual cortex for this stuff. Let me go back here. Sorry, I thought that was opening up in a new window. Okay. So let's talk a little bit about the visual cortex. So in your eyes, you have rods and cones. They convert these light signals into electrical signals. Those signals are transmitted back to your visual cortex, which is way in the back of your brain. Here is your visual cortex. Way back here is your visual cortex. And it's kind of broken up into different layers or regions. And because we're so good at numbering them, we call them like the first vision one is called V1. The next vision one is called V2 there. So we have these different what we call the primary visual cortex regions back here. And we have the first set are made up of simple cells that detect light at a certain angle. So they might be looking at light at a certain angle. So they'll have some negative areas and some positive areas. So if light goes, so the yellow is like the excitation going at this pattern, and it's including some negative sides and some positive sides, and the amount of negative area and positive area is about the same. So in this case, we get really no signal here. But if the light that we're looking at on our image, this one part of an image, lines up with the receptors of this cell, where we have positive and negative here, then we'll get a strong response from this sort of stuff. We also have some cells that don't just reply or respond to light in a certain direction or a line in a certain direction, but will respond to a moving line across our fields here. So again, our brain is really, or our visual cortex is made up, and again, they've done extensive mapping of this here, where we've got whole columns of cells in our visual cortex. Each column will be trained to recognize like a flat or a line or a vertical line or lines at all these different angles here. So again, this would be like a mapping of our whole visual system, but only looking for vertical lines or only looking for horizontal lines or lines at a 15-degree angle or a 30-degree angle and whatever. And again, we have these mappings for the left eye and the right eye and stuff like that. So we have these, it's really interesting what we call these filters that are applied to this system. And again, this is just how the human brain works. So we're going to try to mimic that on the computer system for this. So again, we're going to try to look at how we can set up these neural networks to recognize first some fine features like edges and stuff like that, and then some more complicated textures, some more complicated patterns. And then maybe parts of an image, and then finally objects and stuff like that. So again, we'll be training these sorts of filters to start with low-level ideas and build up more complicated features from that. And again, here's another view of the visual cortex, where again, at V1, we're just detecting edges or lines at different orientations. At V2, it'll take input from that and try to construct like shapes or stuff like that. V4 maybe is trying to recognize more objects there, and the IT region again is trying to recognize faces, actual people or stuff like that. So again, we're building up from very simple objects to more complicated objects to more, even more complex objects, and then finally some recognition sort of idea with this visual cortex idea. So again, we've known, and the visual cortex has been heavily studied for a long time. So that's what we're going to do, and we're going to look at how we apply these regions. We're going to look at some different features here. I'm going to jump to this image kernel stuff and how this works. Okay, so zoom in just a little bit more. Okay. So we're going to start with just a black and white image here. And in the computer world, those black and white images or grayscale images are recognized by simple values between 0 and 255. So on the left side here is our numbers. White, bright numbers are like 200s, 250s. The higher the number, the brighter the image. Dark portions like over here are low numbers, usually like below 50, a 40 or 30, maybe a single digit sort of stuff for our image. So that's our image, is these numbers between 0 and 255 here. And you can kind of see the face and how that works. And again, now this is just grayscale. Now we manage color basically the same way. With color, we just do 3 different layers. RGB generally is a good way to think of red, green, blue for this. So a layer of the reds, a layer of the blues, and a layer of the greens. And then to make all these different colors, we mix different amounts of reds, greens, and blues together to get our different color values for this. So how are we going to apply a filter to this? We're going to create different what we call kernels or filters that we're going to apply to this. So this is like an edge detection filter here. So it's a 3x3 matrix, and we're going to apply that 3x3 matrix to this image here. So we're going to start in the upper left-hand corner and apply that 3x3 matrix here. So we're going to take the, let's see if I can, we're going to take the top pixel, the top left pixel in that image, and we're going to multiply it by 1. And again, so this image here shows that the top thing is going to be multiplied by 1. The one below it will be multiplied by 2. The one below that will be multiplied by 1. Then we'll go over 1 to the right, and the pixels will all be multiplied by 0. And then we'll go over one more, and it'll be multiplied by -1, -2, and -1. So if we go up here in the top left, see if I can get there. Oops. The top left pixel value is 206, and we're going to multiply that by 1. Below it, the pixel is even brighter. It's 244, and we're going to multiply that by 2. The next pixel is 192. Then we do the 3 middle pixels, and we're going to multiply them by 0, which basically ignores them. So each of those values are going to be multiplied by 0. So that's going to be 0, 0, 0. And then we'll get to the pixels on the right side here, and those will be multiplied 247 times -1, 137 times -2, and 75 times -1. And that'll give us a result here, a value, and in this case it's 290. And then we'll just, our pixel values have to max out at 255. So if it's above 255, we're just going to say it's 255 for that value. And that'll be a very white pixel. So on the right, you can see the red dot shows a white pixel because that'll be 255 here. Now let's go over. So then we'll shift over 1 and we'll apply this again. We'll apply the same filter, but shift it over just 1 pixel. And so we have 255 times 1, 161 times 2, 154 times 1. And then 0, 0, 0 for the middle 3 pixels, and then 245 times -1, 245 times -2, and 200 times -1. And now we get a value of -252. And again, our values have to be between 0 and 255. So if it's negative, we're just going to truncate that to 0 there. And that's black here. So far, we've got a white pixel and a black pixel here. And again, we can we're going to then keep moving our filter over, calculating, move it over, calculating. So the amount we shifted each time, each time we move over, we'll shift it over. And we'll call that the step. Generally, we'll just step over 1 each time, step over 1. And again, after we go through this whole row, get over here, we'll go back where we started, and we'll step down 1. And then over, and go over. And then again, come back here, and we'll step down 1 more. So generally, our step will be 1 there. We have a 3x3 grid that we're applying to this. It's going to be confusing at first. How are we doing with this? Online people, is this making any sense?
What's the end goal?
So again, we're trying to apply different features. So like here, we're doing, like this one is an edge detection. So you'll see the face there, and what on the left, on the right would be a vertical edge detection thing. So we're just detecting one feature of vertical edge detection. Now we could switch the filter to a horizontal edge detection. So now it's detecting horizontal features here. And we used to program our own features into this. And that's what these were. I mean, these are well-known features that we used to have to program in the different features. Now the AI will learn, we'll just say, create a bunch of 3x3 filters, and it will learn what will be good features to use for this here. So it won't just use the top symbol and or the emboss, or there's these different features. It will learn some really interesting, well, it'll learn features, these values, these parameters in here, will be learnable. So these will be like the weights in our neural network, for this. So we'll create a neural network where this layer will be connected to the next layer, and these will be the weights for that. And the computer will learn how adjust these weights so that it recognizes images better. Now, have any of you actually used like an image processing program like Photoshop that has filters in it? I don't know if anyone, do you use Photoshop anymore? So like Photoshop has filters you can apply. You can apply the emboss filter or the edge detection filter to an image in Photoshop. And again, it's doing this sort of stuff for this. Again, we're gonna apply this stuff to an image. Well, and again, rather than selecting a like a blur filter like this, we'll have the computer learn what filters to apply. And again, this comes back from the human brain, where the brain is detecting lines at different angles. It's detecting low-level features there. And so we're going to try to set up a neural network that uses this sort of feature mechanism kind of to set this up. So this is one kind of filter. This 3x3, just a normal filter. Another filter or layer will be called a pooling filter here. And with a pooling filter, we're going to take a 2x2 grid, and what we'll often do is what is called max pooling. So we'll apply this 2x2 grid to this bigger image. So the pink section here will apply. That'll be these 4 pixels, and it'll be max pooling. We'll just pick out the largest value here. So 5, 34, 32, 54, the largest value in the pink region is 54. So we'll create a 50, we'll bring that over. Here, 78, 156, 221, 221, the largest value is 221. We'll bring that over. So here we're taking the same filter, but rather than a 3x3, we're using a 2x2 filter. And rather than stepping over 1, we're stepping over 2. So again, and we're stepping down 2. So here's the max here is 253, and the max here is 119. So we start with this 4x4 image, and we end up with a 2x2 image, a much smaller image. And this is what we'll do to kind of reduce our image here. And the idea maybe is like, let's say you're detecting things and you're detecting like an eye or an eyebrow or something like that, different features here. You just think there's probably an eyebrow in this region or this region. And so and the higher the number, the more likely it is that eyebrow, hopefully that feature exists. So you just want the max of this. So we're saying like, oh yes, 200, it looks like there's an eyebrow in this region, where maybe not so much in this region because the highest value is only 54 for this. So again, we'll use this max pooling, and max pooling will take an image that's very big and shrink it down into a smaller size image for us. Okay, so let's look at some of these. I'm going to look at this data science blog article and talk about a little bit how this works. So we're going to take an image, and again, we're going to apply these filters, like these 3x3 filters to the image to generate a new layer. So we'll have the computer learn one filter and apply it. But we want to recognize multiple features in this image. So maybe we'll recognize 3 or 10 or 20 different features, different filters. So we'll say, tell the computer you have 20 different features or filters you can learn. and each one will generate a different type of image here. So just like here, if we change, this is the blur filter and we get this. This is the Sobel, Bob Sobel, we get this. So again, each filter will generate a different image. And that's what it's kind of showing here. Each layer is like a different filter applied. So we've applied a bunch of different filters. Now the image is the same size because we're stride, our step is only one here when we're applying this. Then we do this max pooling, and that shrinks this image down to half the size. So we do a max pooling layer, shrinks the image down, and then we apply a set of filters again. So we apply these filters again, different filters here. But now 3x3 filters will cover kind of a bigger area because the image is smaller here. So we get that, and we'll do max pooling again and shrink our image down. So again, we go between these filtering layers, 3x3 filtering layers, and then a max pooling layer, and a 3x3 filtering layer, and a max pooling layer. And eventually we get down and we'll just feed this through a normal neural network, a fully connected neural network with 3 layers and the outputs. And in this case, like it's trying to predict if there's a picture of a dog or a boat or a bird or what. So again, this talks about how we have our images. Those are converted just to numbers. And again, then we're applying these filters. Let's see if I can make this a little bigger. So here's our image in green. Here's our filter, our 3x3 filter in orange. And then we're applying our filter to our image again and again. So here's the top left corner, shift over one, shift over one, shift it down, down, down. And then we get our new image here. Now, sometimes the new image will be a little smaller than the original because of the edges here, but sometimes we'll buffer the edges here. If I look at this, here I can actually go over and do the top left corner, not 3x3, but it'll maybe assume that like around the edge, the border is maybe all white pixels or all black pixels or something like that. So there are some times where we don't want the image to shrink as we go for this. Okay, so we applied our filter here. And again, these are different types of filters out here. We apply our filter and we get our feature map or some version of that. And then we'll apply a different filter and get a different feature map. So we have multiple feature maps that are detecting multiple different things from our image features. And again, we talk about the stride. As we move the filter, how much we shift it each time. Often the stride is 1. If we shift the stride to 2, our resulting feature map will be smaller, half the size. We talk about padding. And do we pad the pixels along the edge of the image? There's different ways of doing that stuff. And then we have this special value for calculating the output of this called rectified linear unit value. And what it is doing is summing up all the inputs, the weighted inputs. And if the sum of the weighted inputs is negative, we're going to return 0. Otherwise, we're just going to return its value. I'm not going to dive too much into this value. There are different, I don't know, when we did neural networks, there are different activation methods we use, but this is the one that's really become popular these days. Yeah, it works very well and very fast for this. So, okay, and we talked about max pooling here, calculating this stuff. So we talk our image, we do our convolutional filters with rectified linear units, we do our max pooling, and we'll get our results. And we're going to layer this all together for this sort of stuff. Okay, I'm going to jump into this online example of this sort of stuff. This is convolutional JS, which is from Stanford, which will show us different convolutional neural networks and how they work here. So this is a neural network. And again, when we create them, we'll create them a little bit different than this, but this is an example of it where we start with some input image. We then specify how many convolutional layers we want, or we specify we want a convolutional layer. We then specify the size. And here they're actually using 5 by 5 rather than 3 by 3 filters. How many layers or filters? We're going to try 16 different ones. What is the stride and what is the padding and what is the activation function? So you can specify all of that. And then we're going to use a max pooling layer with a stride of 2 and a size of a 2 by 2 with a stride of 2. We're going to then do another convolutional layer, 5 by 5 filters. We're going to do 20 filters. We're going to have a stride of 1 and a padding of 2 and use this rectified linear units and keep going here. And we're going to then combine, train this model on this data. So what data are we using? We're using the CIFAR 10 data set, which are 10 different images of things like cars and horses and I think frogs and stuff like this. So this just kind of shows you, here's our image. Here, let me see if I can pause this. Let me pause. Okay, so here's an image of a bird here. And then here's all our different, our 16 different filters or feature layers that we applied to that there. And then we're gonna shrink this down with, oh no, this applies the rectified linear units. And now we're gonna do max pooling to shrink it down and then do more convolutional layers here and then do rectified linear units. And again, more pooling to shrink it down. So although we started with a 32 by 32-bit image, by this point, we're an 8 pixel by 8 pixel image. But we have 20 different features we're detecting in that there. And eventually we get down to a 4 pixel by 4 pixel image, and then we feed it into a fully connected layers, and we predict the results. Now I'm going to keep this going again. Now, all these filter layers are parameters we can change using our like back propagation, our algorithm. So we will feed this, we'll show it a picture like this of a horse, and it will try to predict what it is. It thinks maybe deer or bird or frog. None of those are correct. So we will adjust all the filter weights to improve this using what's called back propagation method. And then we'll show it another image and have it recognize it. So here it's thinking, it shows this image. It thinks it's a car, which is correct. It also thinks it could be a truck or a ship there. So originally, it's going to get a lot of these wrong. Its accuracy is only 27% right now on our 200 test images. But as we keep adjusting, showing it new images, adjusting the filter weights, showing it more images and slowly tweaking the filter weights, the filters will get better and better and better. So it'll start recognizing this as a frog and this is a truck. This is a truck. This is a ship here. So it'll get better, but eventually it'll learn better features in here. It'll develop ways of detecting better features, choosing better feature maps so that these features are kind of all filled in here. So it'll do better at detecting these values here. And we just need to let it go and keep updating its weights and doing it. This is a measure loss, the measure of how much it's off, how much it's wrong for each time. And the amount of times or the distance it is off each time is actually getting lower and lower. It's learning a little bit better each time. Okay, I'm gonna stop that. That's again what we're trying to do with this sort of neural network or convolutional neural network. It's has parts of a traditional neural network, but it has these special convolutional layers, these filter layers, and these max pooling layers built into them. So now, where do we see these things? Colorization, detection, those sorts of topics. This was big back, 10 years ago. This was really cutting edge sort of stuff with this. So I'm going to open up a notebook, and you might want to open up the notebook too. So again, we're just in learning resources. We've scrolled through this stuff. We're down to convolutional neural network notebooks. Now this first one, I'm just going to show you as why we need something called GPUs, graphical processing units. So I'm going to open up this notebook here to start with. So again, here's our notebook. I've already run this here. We import a bunch of libraries here. We're now using libraries from TensorFlow here, which will bring us lots of layers. So, and we're now adding some layers like a convolutional 2D layer, a max pooling layer, an average pooling. So we have some new layers that we're bringing into this here. We're going to bring in a set of data. This uses what's called the minced data, which is just images of digits. It was one of the first training sets. It was created by the post office to recognize zip codes here. And one of the first automations were done was to process envelopes and recognize zip codes off of envelopes so we could automatically route letters around. So there are 42,000 images. Each one is only 28 by 28 pixels here for this. And so here we're taking our data, breaking it up into a training data and a testing data here. The output has to be, remember our one hot encoding, the output has to be a digit between 0 and 9, but we're using one hot encoding for that. So like 3 is encoded as 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. So there's just one hot value there. Everything is 0 except for that value, and that's the third value. And you're thinking, that's the fourth value, Tom. But remember, we're doing digits, 0, 1, 2, 3. 0, 1, 2, 3. So that's 3 there. So yeah, as we break our data up into training and testing data, we are then going to create our network here. We're going to start with a 28 by 28 image. We're going to apply 8 filters, 3 by 3 filters. We're going to apply 8 filters again. Here, we're going to do some max pooling to bring it down to a 14 by 14. We're then going to apply 16 filters here, and then we're going to process it there. So here's our actual code for this. We use our input, and our output is 10. And again, here's we say we want a convolutional. We want filters are 3 by 3 here. And this is actually doing 100 of those filters. Our activation is this rectified linear units, and padding is the same so that it doesn't shrink it down at all. And again, we can actually modify this in different ways, but this will show us the size of our network. It also shows us how many weights we can modify. Each filter has these weights in it, so we call those parameters. So this has 180,000 parameters. So there's 185,000 different values that we can modify here. This is the same thing you'll hear these days when we talk about large language models, and they'll have like a billion or a 7 billion model. That means 7 billion parameters are in a large language model. So Although 180,000 seems like a lot, when we'll get to much larger networks, and we'll see much larger networks out there, many more parameters. So that's just how many different numbers can we adjust, can we learn during our learning process. This has 180,000 different values we can adjust here. So here's our actual training. We created our model and we called it NN, for neural network, I guess. Very great name for it. And then we say NN.fit. We gave it the training data, the X and Y training data. We're going to train it for 10 epochs. Here we do some callbacks to do some stuff to it. And then we are validating it. We give it the testing data to see how it goes here. Now, accuracy, it starts at only like 80% accuracy, and slowly it gets up to almost 99% accuracy as we go through here. Now notice every one of these, it takes about 200 seconds. Later it gets a little faster, 140 seconds. And again, if I could run this again, I could. Let me just run this again so you can see this. But remember, this is taking about 200 seconds to do it. So this is one epoch, of 10. And we should be training this probably for more like 100 epochs, but we just don't have time for that. So again, this is running here, and training is taking a lot of time for this. So now, so far, there's 1,182 images it's going to process during this epoch. And so far, it's done 300 of them as I'm talking. And we're still waiting for it to keep going here. So it's only about a third of the way through. So this training is just going to take a long time. And so now we're getting these models where training is going to be a long time. Now, as we train these, what we'll want to watch for is the model accuracy. So here's the model accuracy on our training data. It starts low, like at 80%, but slowly climbs. And even as we keep going, it keeps getting better and better. As long as this accuracy is still going up, we probably want to keep training it. But now the blue line is our training data. The orange line is our testing or validation data. And if you notice, that is kind of plateaued. So maybe we shouldn't be training anymore, because we might be memorizing our training data more, but for data, it's not images it's never seen before, it's not really getting that much better at those. So this is our model accuracy. We also sometimes look at the loss. This is how much, what percent of the time it's wrong. And so if it's wrong, it can adjust its weights, it can learn. But when the loss gets really close to zero, it can't learn, because it's getting if it gets 99% of them right, it's not very few times is it adjusting the weights for that. Okay, everybody's taught. Let's see if it's still, we're still going through this first image here. Okay, 144 seconds here for this. So again, it is likely taking minutes to get through each one of these values. Okay, I'm going to show you a faster way of doing it, because that's too slow. So I'm going to go, that's this notebook. We're going to go to this. I'm going to open up this notebook here, this convolutional neural network example. And the first part of this is this same missed data. I'm just going to run this all to start with. So we're going to import our data. We're bringing in our digit data here. We're looking at that. We're creating our layers for that. We're defining our network for that. And this is a little smaller network, 8 features, each 3 by 3 for this stuff. And working this out. I'll just warn you, there's been an update to this. I think I've caught all of them, but if you run this, and you get an error with this what's called this model checkpoint where it saves this. This has to have a certain name to it. And so this is just a relatively new thing in the last few months. So if you get an error in a notebook with that, you should just follow the recommendations. It'll change this name appropriately. But I think I've got all the current ones that you're using fixed with that. Okay, so now we're training this, but now notice how fast this training is going. This is taking like 4 or 5 seconds, where this one is taking 200 seconds or more. So why is this one running so much faster? Well, it has a slightly different network that helps here. So our model is a little smaller, only 100,000 things it's learning. But what really makes the difference is how we're running this. If I go down to runtime and go to change runtime type, this is running on a T4 GPU, which is very fast. Where this one is running on just a regular CPU, which is really slow. So you'll want to try to run these things on a T4 GPU. It used to be we could run GPUs all the time on these things, but Google has now kind of throttled it back. So you only allowed so much GPU time every day here. And so you might run out of GPU time when you're going through this. So I'll just warn you, let me know. And again, really hard to sometimes to tell under the hood how much GPU time we're getting and that sort of stuff. So you shouldn't have to purchase any additional GPU units. Don't worry about, try to, and at least, or let me know how this works and that sort of stuff. Now, there's also this TPU, which also runs very fast, but we'll just be running under a GPU. I'll just note that. Okay, so we're doing this training. I'm actually going to close this other network down. I'm going to stop it, interrupt it, and close it down. I guess I'll just close it for now. Okay, and I go back here. So that's the missed data is one data. Here's another example of this. This is from the Caltech 101 image data set. See if I can, if they've had the new link for this. Caltech moved their images at one point. Yeah. I'll have to update that link. But this is the Caltech images. There are 101 different categories, but we're only doing 20 of the categories here. We're bringing those in. And so here are images of dogs. And most of these actually look like dogs. These are images of ferns here. So we're showing it these different images and seeing if it can classify these images here. So we actually have to read in these images a slightly different way, but here's our network that we're setting up for this. So again, we create convolutional 2D networks or layers with like 3x3 filters and 32 layers. We do max pooling. We do convolutional layers. Students often ask, well, how do you know how many layers? When do you do, I see this time you did 2 convolutional layers and then a max pooling layer and then just 1. And this, here you did 32 and here you did 64, here you did 128. How do you know which layers to do? And that gets away from the science of this and more of the art of designing these networks or engineering. People don't really know, at least originally they didn't know. There's now some pretty good strategies that we'll see, but people just didn't know. People were just trying out, 3x3 layers, 5x5 layers, 1x1 layers. They're trying out different values and stuff. One of the common things is that we often, as we shrink the image, we want to increase the number of features the idea here. So if you're recognizing features, you want more feature layers. So what's one thing is often we start with less feature layers and increase that here. But again, this is a million parameters. So this is going to take a while for this to run. So here, even with a GPU, this is taking a while to run. But again, my accuracy starts at very low, 5%, and it's up here to like 35%. But it should, right now I only trained it for 20 epochs. I should probably be training this for 200 epochs and running it for that long. So again, this is kind of the idea here is we start with a big image, we do some filtering, we do a max pooling layer, we do some more filtering, we do a max pooling layer, do some more filtering, do a max pooling layer here. So this is a common way of setting this up. Now, 10 years ago, we didn't, people first invented these convolutional neural networks here, and we started this. This was one of the first ones, was called VGG16, and this is how it was set up here. We then created more advanced ones like EfficientNet was 2019 with this layer for this. So there are different types of layers you can create. And here we're creating these by hand, like here. But what we'll learn on Thursday is we'll be able to just say, give me a VGG16 network or give me an EfficientNet network, and it will have all the layers already pre-built for us. So you can design your own one, or you can use a pre-built one. So let's jump back into here. So here are the original, the first one that did any convolutional neural network, what was called AlexNet back in 2012. And there was this competition called ImageNet, and it just blew every competitor away. Every year they were doing it, it just blew every competitor away. And everyone just was amazed by it in 2012. And so then everyone else started duplicating it. Here's AlexNet here. So here's VGG16 and VGG19 that came out later. Google introduced their Inception network about the same time. And again, people were trying lots of different things. Google was thinking outside the box. Rather than just having their single layers here, Google said, well, we're going to take our previous layer. We're going to do a 3x3 convolution, but we're also going to do some 5x5 convolutions and a 1x1 convolution and a max pooling all together. And then we're going to concatenate those. So they did something called these inception layers. So every one of their layers was actually all these different filters applied at once there. They expanded it to this even more complicated system of layers, and they had really good results. So like here's one, all the layers for one inception module here. These networks got really big and training was really hard. So some people introduced what is called a residue network, where you'd have the connection from one layer to another, but then you'd also have these skip connections that would connect directly to a layer 2 or 3 layers ahead. Sometimes called a residue connection, sometimes called a skip connection, something like that. So these connections would jump ahead. And so these were generally called residue networks because they had this. And so a lot of people introduced these residue networks for this. There are lots of networks out here. And again, we started having many more parameters, and the training time took a lot more for these networks. So starting about 2010 to 2020, our growth in the speed of our hardware, the number of parameters just took off, and it's seemed to increase a lot. So what we'll see on Thursday, we'll do transfer, and this will be the project for the week, for this week and next. Here is we'll start with a pre-built network like VGG 16 here. And what we'll do is we'll cut off the top of it where we're the last part of the training. So here's our input where VGG or whatever network you have will be pre-trained on a bunch of images. So it'll get all these filters at each layer trained up. So we'll have all these wonderful filters. And then we'll say, okay, can you recognize this as a cat or a dog? So this final connection layers will do the, given these filters, can you tell if this is a cat or a dog? We will get rid of those filters and we'll apply our own final layers to that. And what we call that is transfer learning here. We'll use most of the network that's been pre-trained and just add a little bit, a few of our own layers on top of it for this. And we'll talk about ways of setting up this sort of stuff here. I'm not gonna, there are some new types of layers and stuff. I'm not gonna worry about those today because we have that. Okay. It's so hard to try to figure out which of this stuff to learn because of this and how to pack this all in today. I'm going to just mention some things about bounding boxes and image segmentation, but we're not going to go into it too much this year. So just so you know, there are a couple ways of doing image detection, and one is just to see an image and say, that's a cat, that's a dog, and or that's a person or whatever. And that works well if there's just one thing in the image. But often our image will have multiple things in it, like this one does. So we do train networks now to not just we won't, but in class, but you can tweak these so that they can recognize multiple things and they can draw boxes around them. So your output is not just that's a dog, but that's a dog and here's the location of the dog. And we generally specify like, we might specify the upper left-hand corner and the lower right-hand corner of the dog image, or the center of the dog and then how big the dog is. One of those values. So again, we'll say this is the dog here. And so our output is not just dog or cat, but dog at this location with this size, and bike at this location with this size, and car at this location with this size. But in order for this to work, we need training data for that. We need people to identify all of these values and where there's a dog and a cat and how much of that. At some point, we paid grad students to go through tens of thousands of these images and draw boxes around them and label them all there. You've actually probably done that before. Have you done a CAPTCHA where it says, identify the motorcycle, or identify the stoplight, or identify the crosswalk? That is Google using you to train its image and figure out where the different values are on these things. So that's one. Okay. So again, there's different ways of specifying this. Again, so the output of this might be a dog at this location, a bicycle at this location, a cat at this location, or a car at this location for this. We've done Kagel's sea turtle, and largely because we just love, everyone loves sea turtles, right? Kagel has had an original challenge to detect sea turtles here, and it's still out there. This data set's still out there. So it's a bunch of sea turtle images with boxes around the turtle faces there. Now, boxing only works so well. The other thing we see at times now in better situations is segmentation, where we have an image and we'll take our original image, we'll regenerate it, but we'll just highlight pixels saying this orange, anything orange is a person, anything blue is a car, or something like that. So this requires us, here, the output is not, I mean, you see this output as an image, but the output is really just this. This is the output. But if you can generate a whole new image, if you can take in an image and generate an output image, then you can do segmentation. So this is what we're seeing here with sort of stuff where we're doing it. Now, in order to do this, we need a special network, often called UNet, where we're taking an image, we're shrinking it down, again, doing filters, max pooling, filters, max pooling, filters, max pooling, and this would be the end of our kind of traditional output convolutional neural network. But instead, we're going to generate an image. So we're going to do reverse max pooling and reverse max pooling and filters and stuff like that up to here. And then we're also going to add some special input so that this image will be fed into this image too. And again, our output will be an image here of a certain size for that. So we'll take an image, we'll condense it into some meaningful representation, and then we'll regenerate the image for that. And this is important because when we start looking at image generation techniques, how do you, Gemini, I want a picture of a snowman dancing on the moon, sort of ideas. We'll use kind of structures similar to this at times. So, okay, I'm not going to get into loss functions there. Okay, so what do you want to do? Well, you want to do? What do you have to do? Maybe what is Tom forcing you to do this week? Okay, so on explore activity, there are more choices because I have 2 weeks of explore activities here. So again, just choose one of these here. Choose one of these options. Now, some of these will be just more convolutional neural network sort of stuff here, and how you do those stuff. Most of the main systems have created like a pre-built visualization pipeline so that you don't have to set up your own layers and that sort of stuff. So I think like Azure, Microsoft has their custom vision system service. Amazon has their Amazon recognition system, which is their image recognition system here. So some of this will show you more advanced features that have kind of wrapper around these sorts of convolutional neural networks. So again, you've got to do one of those. Thursday, we'll go through this notebook here, and we'll run this. Now we'll get it started on Thursday. This is going to take us time to do. So we'll probably not get through it. I mean, the training will take a while to go through on this. So we'll set this up. And again, discussion this week, anything image generation or recognition related, X-ray, cancer detection, facial detection recognition, satellite image processing, the DNR and places like that, do really cool things with forest generation, hunting land, farming land generation, and processing images of satellites there for this, any sort of things like that. And again, any sort of cool image generation stuff. What are you using? Are you generating any images? I always have to ask my wife what her latest image generation tools are, because she does a fair amount of publishing and uses a number of tools for different newsletters and stuff. So I'll talk to her before. And so next week we'll learn how those things work, but it'd be fun to play with some of them now. I would even include like in game design, we do the 3D model generations. If you find a nice one that generates 3D models, I would accept that at this point. They're like blender type models, so something like that is fun to see at this point. So post those to discussions. I by Thursday I'll have the assignment up. It's still linked here. I haven't updated it all. I mean the project. So the project, let me jump in here. Will be again applying these convolutional neural networks, these pre-trained ones, to one of two things, either humpback whale identification here or pneumonia identification X-rays. So we have these two different data sets. We're trying to apply our images here. So I really love the humpback whales because a couple of years ago, I was out visiting my son out in Washington State, and we went on a whale cruise. And usually, you just see killer whales out there, but we got to see humpback whale. And I didn't know this, but when they dive, their tails show up, and they take pictures. And our guide, took pictures of this humpback whale dive, and then he submitted it to these projects. And every whale out there, every humpback whale, or lots of them, thousands of them, have different patterns on their whale tails. And so they can look at that and go, oh, this is that whale. And so the person was able to, they couldn't do it live at the time, but they were able to email or, send out later on what the name of the whale that we saw out there was, which I thought was really cool. So, and you can help fix people's health if you want to and save people's lives. But, you can also identify whales. So you have to decide where your values are in there. My brother's a doctor, a physician. He saves people's lives. So I'll leave that up to him. He can do that. I'm much more interested in whales. Sorry. So, okay, so that'll be available as the project, and hopefully by Thursday I'll have that. It's basically there. I just have to tweak and make sure it's all working with the new with the changes from last time. Okay, questions on this? So feel free. I'm going to try to leave you a little early. I really recommend you just watch the MIT video here. I think that does a much better job of walking through everything than I do here. So they have great visualizations. So I'm going to leave you hopefully so that you can just sit down and watch the MIT video. Sound good?